Hello, everyone. Welcome back to zkStudyClub. Really excited to have everyone here for another edition. Today, we're very excited to welcome Michele Orrù, who's going to be talking today about techniques to minimize foreign or non-native arithmetic in zkSNAR. So I think he'll be introducing a couple of his co-authors. Michele, thank you for being here. Really appreciate it. The mic is yours.
Hi, hello, everyone. Hope you can hear me properly. This is joint work with George Kadianakis, who is just next to me and will assist me in any question you might have, and Mary Muller and Greg Zaverucha, who is at Microsoft Research, and he's a bit more senior than this community. He invented the KZG polynomial commitment scheme, for instance, which everybody I think here knows about. And yeah, I think in this paper, a lot of other people participated, like Melissa Chase, like Trevor, like Andrea. And yeah, so I'll be like, it seems that this paper has a bunch of different applications, and hopefully I'll try to cover at least some of them during this talk in a way that is clear to everyone. And yeah, as it was said, this paper, which is 2024/265. And yeah, this paper is essentially a combination of three different tricks. The first one is about proving that two commitments are to the same values across different fields. So imagine, and this was our use case at the beginning, imagine that you have a credential or a Pedersen commitment over curve 25519, and then at some point you're like, oh no, now I want to migrate all these commitments to BLS 12381. How can I do it? And so this is a very efficient proof to prove that you have a commitment to the same value, and it can be easily generalized also to longer commitments or other different values. Then we prove that this can be done with a simple Schnorr proof. And there was some previous attempts before, some of them from Melissa Chase, some others from Waken. But the first one was using more Garble circuits technique, and the other one was using Fry proofs, which are sort of a bit more cumbersome and heavy. Here, we just do it with a single sigma protocol using a technique called rejection sampling. The second contribution of this paper is also something that comes pretty often, and it's this sort of mix of algebraic and non-algebraic statements where you want to prove that you know a secret key associated to a public key, and then you want sometimes to prove that, for instance, this secret key is in a Merkle tree. And so here you have got these, let me see if I can have a laser in here. Well, I don't really know how to do it, but yeah, so the idea is that you want to, we give you a way of mixing this algebraic statement with this more symmetric key statement. And the way to do it is that we defer, we have a single big snark proof for hash pre-images, which we know how to do it, and we already have gadgets for it. And instead of having in the same circuit also the proof of the scalar multiplication, which seems to be very heavy and cumbersome in modern snarks, this we defer to different Schnorr proofs. And the trade-off here is that we need to add another hash pre-image proof in this protocol. And the third and last one is that oftentimes we also want to mix secret key operations. So differently from before, it's not public key operation, it's more like secret key operations like AES, and commitments. So we have, say, a Pedersen commitment to a value, and then we want to prove that this message that I committed to as Pedersen is also encrypted as an AES ciphertext. And the cool thing that we get with this is, for instance, verifiable encryption that is made very easy, because then you end up only proving things about the Pedersen commitment rather than the ciphertext of AES itself. And this is also compatible with other generic snark techniques that we know of. Okay, so this is sort of the initial framework, and all these protocols are very easy. Oh, there, let's go.
Oh yeah, if there's a question, we should just remember to read it out for the listeners on YouTube.
Right. So the question is, what if X is larger than one of the moduli? Yes, we will cover this case, and rejection sampling really tries to deal with this. I will go over it in a sec. all of this is done with using very simple Schnorr proof. Surprisingly, also, this AES proof, despite obviously you can do it also with compressed sigma protocols or mono-involved techniques, the way that we present it initially in the paper, because we want to have something really, really simple, is just using Schnorr proofs, which is sort of ironic, but we will see then how it plays out. So in terms of notation for the rest of this study club, I will talk mostly about 3 message protocols. I'm gonna define the first message as commitment, called K, second as challenge, and the third one as response R. And yeah, in a classic Schnorr proof, the way that this is done, the scenario is that I want to prove to you that I know a secret key associated to a public key. So what do? I select a random element that is going to be useful for zero knowledge later. I commit to it, namely I create an ephemeral key, I get a random challenge, and then I compute the response as the line that goes through K and X, where X is my secret. We know that these protocols have at least 2 very important properties. One of them is special soundness, which essentially says that this morally speaking is a zero knowledge proof, and it satisfies very strong soundness properties. And the soundness is defined, roughly speaking, as if I have if the proof is a really a good prover, then you should be able to reply to many different challenges with valid responses. And in fact, if I have 2 protocols that have the same commitment but different challenges and responses, it is trivial to recover X from it. And this can be proven then using rewinding techniques or in the algebraic model using straight line extractor, but that's another story. So this protocol, I just want to convince you it's sound, and this is some sort of a like 101 lecture about Schnorr that will be useful for how we frame the rest of the talk later. It is also zero knowledge, namely we do not reveal any information about little x in this protocol. And the reason for it is that it is always possible to create a transcript that is done by a simulator that does not know anything about X itself. And the way to do so is to sample the response and the challenge and then recompute the commitment from it in such a way that it satisfies the verification equation. This is sort of all known. I'm just trying to set up the notation and get us the grips of it together. So this is our starting point. And from here, I want to start with the first of our targets, which was the zkDLEQ. And again, here the scenario, I'm slightly simplifying it. So I just want to prove to you that I have 2 values of which I know the discrete log across 2 different groups, and that their discrete log is the same. The scenario here, in my case at least, was that was this infrastructure change, and then you wanted to change the public keys from one secret from one group to another, and we wanted to prove, for instance, that X was the same 128-bit value. So in order to simplify even more the problem, I'm going to assume that X is a somewhat small secret. If X is not small, there are generic techniques by which I can sort of split the commitment in 2 and then run this protocol twice for each of the 2 parts of the commitment. But for now, let's just keep it easy and simple. I have 2 public keys in 2 different groups, and I want to prove that they have the same secret. And so the protocol is going to go roughly as follows. I have, again, my commitment. I have, again, my challenge. And I have, again, my response. And I'm going to send a commitment, bk, that is, again, little k times the element over p and the element over q. So I'm, again, sending an ephemeral key over the 2 groups. And normally what I would do is that I, hash k in here, which is, again, the 2 elements. And then in a normal Schnorr proof, I would also send you the response as this one. And then I would check that it satisfies the verification equation. The idea for this protocol, is that if X is small, and C and K are also small, then think about this over the integers, R will be also small. So there is so if R is small, then and C is small, then K and X are small. So coming back to the question, the idea is that if we have a way of assuming that if we know that over P, for instance, X is already small, then if we think about the argument only over the integers, we can perhaps hope to show that X is not wrapping up in the second group if P is less than Q. And the way to do this is something called rejection sampling, which was a technique that was introduced by Lubashevsky in 2008, in 2009, and then done by other people in the same ANS lab in Paris. And roughly speaking, this technique is thinking about the following. It's used a lot in lattice-based techniques, by the way. And the idea is, again, that if I choose the challenge to be small enough and K to be also small enough, then I have some hope of making sure over the integers that X is also small. However, I must make sure also that K is still hiding X. So there is really a small window of bits where K is still hiding X, not revealing information, and we're still able to prove that X is within a window where it does not wrap up modulo P or modulo Q. And so we have essentially these parameters to deal with. We have the number of bits of X. We have the number of bits of the challenge. And we have the number of bits if the protocol of like margin where we can expect the protocol to stay within a random distribution, which I'm going to call it the failure probability. This part over here. And so the way that we do this is that we take, instead of just taking a random C in the field, we just take a C that is small between 0 and 2 to the C. So that we are taking a challenge that is potentially smaller, and obviously this will affect soundness. In particular, soundness will have an error that depends on 2 to the C. K, instead of sampling it uniformly random, we will sample it from 0, from 2 to the X, the number of bits of X, plus the bits of the challenge. Oops, bit of the challenge plus the bit of failure probability. So let me show you what's happening here. Let's think about this operation again for computing the response over the integers, and try to compute the bits. So if C has number of bits B of C and X has number of bits B of X, then this multiplication will give us at most BC plus BX bits. And then we have B of K, then we have K, which has number of bits B of C plus B of X plus B of F. And as you can see, B of F is really sort of an extra mask that allows us to have zero knowledge, because in the paper, we will show with a lemma that is really inherited by these previous works, that these extra bits that I'm putting really mask completely X. And whenever I add them, then R will have, roughly speaking, BC plus BX plus BF bits, plus 1. And at this point, I will play with these parameters a little bit in order for R to be still smaller than the size of P and the size of Q. So rolling back, rough idea of how does this DLEQ works is that we have two public keys across two different groups. We want to prove that they are for the same X. This X is small. And the way that it works is that I will compute challenges and commitments in a Schnorr proof in such a way that the response will not wrap around. Now, for making even the proof simpler, in general, like in our protocol, we also give up a range proof for X in one of the two fields. So we still need to prove that X is small, but depending on the use case, for instance, in our case, one of the two public key is issued by a trusted third party, so we don't really need to prove anything about it. But in a generic context, if we assume that X is small over one group, using this rejection sampling technique, we're able to show it that is the same value as in another field, and the value does not wrap up, and it's really the same secret key that's used across the two groups. Okay, if this is okay, I will go to the second contribution. But I'm also happy if there is any question over here to take it. Okay, let's go ahead. Sigma bus. The idea here is that I have now instead a public key and a hash function of the same on the same secret key, and I want to prove that it's that I'm using the same value for both. The way that I do this is, again, I have a commitment, I have a challenge, and I have a response. And I'm just writing here how I would do a normal Schnorr proof. Now, what I would do is I would verify that this satisfies the verification equation, and I'm still left with proving, like this is the sort of the starting point, that I still have to prove that also h of x is equal to the hash of x. The idea here is that if the commitment, in addition to the normal commitment, I also send a hash of it, still compute the challenge as before, and then I send back the response, I can, instead of proving everything into a single proof, I can just send a schnorr proof, for instance, of knowledge of k and x, such that the hash of x is equal to h of x, the hash of k is equal to the hash of k, and then test this last linear relation in the group in the field. So I have k plus cx is equal to r. What is happening here? Here, what I'm doing is I'm having a Schnorr proof that is made outside of the schnorr circuit. If I'm thinking about programming this in a sort of a programming in a language that has gadgets for hash functions, and then in a separate zero knowledge proof, I will prove the relation only over the fields, which I know how to do efficiently with arithmetic circuits, and then that I know the two hash preimages of the commitment and of the secret key. Again, the cool thing here is that then I do not have to write in the circuit how to do the public key operation. Now, I mean, if I have to think about why this protocol is secure, is that soundness will depend on collision resistance of the hash function and on discrete log assumptions. For the zero knowledge part, I have to introduce a new joint assumption, zero knowledge. I have to add a joint assumption in here that says that the public key and the hash of x are really indistinguishable from the public key and the hash over a random element. In a way, I need to prove that the hash is not really based on discrete log assumptions, but morally, we can assume that it works for any reasonable choice of hash function and groups. Yeah, like from here, like there are really easy extensions that are possible because I'm using such an easy framework. I can, for instance, just instead of considering a single element, I can think of like commitments. I can think of proving multiple keys, and the complexity of the proof will scale linearly with the size of the response. Here, for instance, I would hash an entire vector. Here, I would hash an entire string of elements, and then I would compute the response as a vector. All these protocols are linear, so they are really prone to be easily extended for many keys and many signatures. Why is this nice? Because then if I have if I have to think about how much does it cost to prove this operation, this public key operation inside a circuit, then we'll be talking about at least thousands of constraints. Whereas if I have to think about hash functions like Poseidon, we will stay more within the range of hundreds of constraints. So in fact, like what we show in the paper is that we have at least a 100-factor improvement over normal R1CS constraints that you might put on over these protocols. Okay, so from here, the last contribution that I wanted to talk to you about is Tinybear. That's a code name, and it's about proving symmetric encryption. Again, what we're trying to prove here is that I have a message and a key, and and I want to prove that the message and the key are what is used to AES encrypt a ciphertext, given the message committed as M and K committed as BK. I'm assuming that these are Pedersen commitments for the rest of this part. And there's been actually parallel work about these in Lasso and in Ulvetana about also how to prove similar relations. And most of the ideas that are in here are also used in these papers. And they were already sort of known even before, I think, in Zcash, who had already to develop a circuits for doing sponge functions and use already some of these tricks. In order to look at these, I will have to tell you a little bit more about AES. So AES is a symmetric encryption cipher that works over elements, over bytes. And in particular, we will study the field, Galois field of 256 elements. So is a encryption over 8 elements. And the block size is 16 bytes. So we will have a state of 16 of these guys over here. And AES is composed of two big parts, the key schedule and the cipher. For simplicity, I'm going to exclude the key schedule from this analysis, but just think of it as operations that are already contained inside of the cipher. The cipher acts in a number of rounds, which are, I think, between 11 for AES, 10 for AES 128, and then 14 for AES 256. And each of these rounds is composed of some sub-operations. The sub-operations that we have are shift rows, which is reordering the elements in the state. So we will have a state that is generally represented as a matrix 4 by 4. And shift rows is just reordering the elements in this matrix. Sub-box. No, well, I mean, the S-box operation. That is very similar to the inverse in this particular field, but it is generally implemented as a lookup table. And then we have the mixed columns operations, which is doing a linear operation over the elements in the state, and then finally add round key. That adds the round key that was generated via the key schedule. If we look at what internally these operations are doing, this is just reordering the state. So it's not really performing any operation over the single elements. The S-box operation is really just looking up in a table. Then I'm just going to call it for simplicity S-box. Mixed columns is going to do a linear operation. And this linear operation can be expressed as a sequence of XOR operations, more precisely, I think, 5 of them. And an operation I'm going to call gal2, that is essentially multiplication by the primitive element in this field. So the matrix for mixed column is of the form 0, 1, 2, 3 that multiplies the state. And what I mean here by 2 is the element in the field that can be expressed as alpha plus 1, for instance. And gal 2 is really multiplying by this alpha. This is to be a bit more technical. And
so it's really treating it's really treating things as field elements.
Exactly.
Like not just as 8 bits, but really as like.
Yeah. For now, we're thinking of them as field elements, yeah. And finally, hadron key is just doing the XOR operation with the state key. So in sums, all AES can be expressed as 3 different functions: the XOR function, this multiplication by the primitive field element, and the SBox function. And SBox again goes by elements over here and then maps them to the SBox of X. Also here, we are just mapping X to alpha times X, and then XOR, where it's taking 2 of them, and then mapping them as XY mapped into X XOR with Y. Okay, and so very roughly speaking, the way that we're going to implement this protocol is just by using one big lookup protocol for these 3 functions, and then prove that all the operations are all these operations are done correctly. Coming back to the question, we don't really encode the at the end of the day, we're really just encoding the elements as numbers modulo p, and we're checking that all these functions are being done properly via a big lookup protocol. Looking ahead, the way that we prove this is going to give us proofs that, at least on this MacBook, which is an M1 Pro, runs in around 30 milliseconds. So it's going to be something very fast. And I think actually there could be even further improvements that can be done that maybe I will leave space more for it at the end of the talk. So how do we look up, given these functions, how do we transform these things into a lookup table? Well, this is essentially Sword ZIPL, and very roughly speaking, the way that I check if a function is equal to y is with very high probability. I just give you a challenge, and then I check that x plus c times y is inside the set of x plus c times f of x for each of the x in the domain. So what we notice is that in here, we have the SBox, which is how many elements are there in the domain, 256. How many elements there are in Galois 2, 256. And here we have roughly 16K elements. What we note also is that the XOR has a particular structure by which, because we're acting at the bit level, it doesn't really, we don't really have to encode this big table. We can actually encode, for instance, 2 tables or that act on 4 bits, and then also have this table to be only 256 elements. So roughly speaking, how does the protocol work? The protocol works that the prover will send a commitment to the witness. What is the witness? All the intermediate states of the AES computation, as I described it here. The verifier will send a few challenges, one for the SBox, one for the Galois multiplication, and one for the XOR table. And then we will be checking, instead of checking the function evaluation, we will be checking that all these elements are in the possible function evaluations that we wanted to have before. And the table where we want to look all these elements is as small as 256 times 3, which I think is in the range of 700 elements. So the table is going to be really small. We have a bunch of elements to test. The elements that we want to check membership for are all the intermediate computations, and those are more in the order of between 1,000 elements. And when you start looking at this number, because you have only 700 elements to look into it, you don't really need the table. The table is really small, so you can also assume that the verifier can be linear time. And in fact, this is what we do in our proof to really squeeze as much optimizations out of the prover and have really nice performances. So the lookup protocol that we are going to use to prove this part is, I mean, this has been already widely used, and it's the lookup from Habok, but it was already present in Bulletproof ++ from Liam and others. And the idea is that to prove that some elements are contained in a larger table, I can just prove that there exists a vector M that I'm going to call the multiplicity vector, such that the sum of the inverse polynomial that has Fi is equal to the sum of mi's x minus ti. So the proof intuition for this so this is already previous work. I think like in what we do in our work is really that we assume that the table is easy to compute, so we play a little bit more with this idea. But internally, what already was remarked by Ulrich was that if f is really entirely contained in T, then there must exist a vector M such that the polynomial that has as roots all the elements of Fi in the initial vector f is equal to the polynomial that has as roots all the elements of Ti times some multiplicity I. So if you think about it, no, because all the elements are internally, maybe some vectors of the multiplicity are 0, so maybe repeated many times. In this case, I will just increment m, and this is really a way by checking the roots that the order is not really relevant. And this is like a technique that was always used in proof in like more in analysis classes, but the idea is that if you apply the log over the two sides of the equation, then you end up with a sum over the log of x minus Fi and the sum of mi times the log of x minus ti. And if you think now about the derivative of this, so I'm really like using loose notation. I'm not even saying where these elements are anymore. But if you apply the derivative to this, you end up really with a final statement of x minus Fi and the sum over I of mi and x minus ti on the other side. And so rolling back, we need to prove AES. We saw that AES is a composition of different functions. We saw that these functions can be correct evaluation of these functions can be done with what I'm going to call a lookup protocol. So checking that a lot of elements are in the same table, and that this relation can be reduced to this other relation over here, proving existence of another vector for which this relation is satisfied. So how does the protocol for proving AES work now that we have all these little ingredients? Well, the protocol works that the prover will send a commitment to all the intermediate computation of AES. We will get the challenge for checking the evaluation of all these functions. And then we will run, at this point, the lookup protocol to check that all the elements are done correctly. How do I do this? Well, I will send a commitment to all the inverses that I'm going to call Q. So Q is the vector that is 1 over Fi. Well, I mean, this is for all of the elements. So it's going to be for the S box, for Galois, and for XOR over I. And I'm going also to send the commitment to the multiplicities, and then they claim the evaluation Y. And at this point, I just have inner products to prove. I have to prove that Q Hadamard product with F is equal to 1. Why? Because I want to prove that the inverse is computed correctly. I want to prove that F inner product with 1 is equal to Y. and that this is the same as the message together, the multiplicities together with the table. Okay, so roughly speaking, in the AES proof, we have one commitment of very small group elements, a bunch of challenges that are being sent, some commitments where again M is really small, and because it's just a vector of multiplicity, and the vector of inverse that is being sent. And given all of these elements, we need to do a bunch of linear proofs. One over here, which is just what I'm going to call a linear evaluation, because the vector of all ones is public and can be computed by the verifier. One proof over here, where the table is also public, because it can be evaluated by the verifier. We saw earlier that is very small. And when we're just left with this proof, for which there are techniques that just reduce it to an inner product proof. So we have the way to do this in general is that you have Q and you do the inner product with a vector of random elements. And F, this is called twisted scalar product. And you want to prove that this is the sum of the powers of Ri. And this can be computed in logarithmic time because it's a geometric series. So really, all this big AES proof becomes essentially a bunch of linear evaluations, which are really easy to do, and an inner product proof. This inner product proof, using something called sum check, that I'm sure has been explained in here quite a bunch of times, can be reduced to 2 linear evaluation proofs. And that's what we do in order to avoid costly inner product proofs. And so it's going to be a linear evaluation over a tensor product over here. I can go into more details of why this is the case if needed. And this is going to be the reduced Y. And these subclaims are also linear evaluations. So all in all, we will have few commitments being sent, a sum check to reduce the inner product to 2 linear evaluations, and then 4 linear evaluations to prove together. Now, these linear evaluations are all over different elements. So yeah, I mean, and this we know how to do. This we could do it with compressed sigma protocols, which are very efficient, give us like log space. Or we can do it even with sigma protocols. But with the sigma protocols, we end up with proofs that are in the order of 80 kilobytes. This is the gist of it. And I just wanted to like maybe conclude this part by saying like what were the optimizations that were used internally to make things a little bit faster and to achieve these good performances. And I guess the first one is that we have many linear evaluations. So we have a linear evaluation over Q, we have a linear evaluation over F, and a linear evaluation over M. And all these different vectors have different points where we want to evaluate all of them. And it is difficult to batch linear evaluations that are, or even multivariate evaluations that are over different points. And the way to do so, that we're able to batch all of them together, is by introducing another round of sum check that takes this evaluation over, I'm going to call it evaluation point 1, evaluation point 2, and evaluation point 3. And these are all reduced to the same evaluation point. I'm going to call it evaluation sum check vector. Let's call it that. And because these are all evaluation across the same point, I can just take a random linear combination of them and just send a single proof. And I think this is what really lowered the public key cryptographic operation that were really the bottleneck in our case, and also avoids us sending 3 different proofs, which also increases the proof size. So I think one of the things that has been also said in a lot of other places is that sum check, for us, it was really a way of reducing the number of public key operations because and increase a lot also and increased a lot of the speed because it's only dealing with field operations, and we didn't have to deal anymore with public key, scalar multiplication, and multiscalar multiplication, added complexities. The second thing that I think was maybe really helpful in our case is that there is this vector f, but I didn't really say well how it was computed. The vector f is if we start from the witness vector I said was all the state of the intermediate computation. So it was maybe the state 0, the first element, the state 0 as the first element, and so on and so forth. And then where these elements over here are the initial AES state metrics. So I have S00 in here, S01, and so on and so forth. And then I'm concatenating with the state at the first, after the first operation is being computed, say the S box computation, and so on and so forth. And this is the state, is the AES metrics as at the first state. So S10, S11, and so on and so forth. And what I want to check is that how do I go from the state of the witness to the vector that I want to look up? Well, this is a linear operation, right? Because I have to take this element and then take C of S box times this other guy. So F can be seen as a matrix times vector operation, where the matrix A is really selecting the points of W that I want to check. For instance, it will be, in this case, it will be 1, then 0 15 times, and then C of S box, and then 0 again, and so on and so forth. And when I multiply with W over here, I will end up really with the vector F that I want. So S00 plus C of S box times S10. Again, so on and so forth. And what we note is that instead of, because I need to, at some point, compute this linear evaluation over F, the way to do it is that I noticed, instead of, I noticed that A, W, and E of sum check, I can, instead of having an additional commitment to F, I can save on it, again, exploiting the fact that the verifier is linear, by just multiplying by A on the other side. So what we have is we will have the prover just send a commitment to all the intermediate state, never send a commitment to F, and then the verifier on the other side will take care of doing all the operations in order to rearrange the challenge in such a way that this linear evaluation will be equal to the desired evaluation over F. This also allows us to really never pay for shift rows, which I skipped before, because it's only rearranging the elements of the state. And we can just, similarly, as I showed here for the S box, rearrange also the elements for computing the shift rows operation over the changed state. I don't know what were the other optimizations that we did. Sorry, the last one, yeah, the last one was, and that maybe I mentioned it also briefly at the beginning, is that if you really look at the XOR operation, it can be considered over smaller sizes of a table. And so that means that we have to commit the vector W, not as vectors of bytes, but as vectors of 4 bits. And so what we end up having is we have a witness that is twice as big. It ends up being roughly the size of 2,000 elements that we have to look up in a table of 700 elements again. And the matrix also similarly has to be changed a little bit, because now we have only the first 4 bits of the state. And then here we have maybe the second part of the state. So we will have more a matrix that has the form 0, 2 to the power of 4, so that we can squash together the first elements, then all zeros again, then the S box challenge, and then, for instance, 2 to the 4th time the challenge for the S box again. And then again, when you multiply, you end up with the right element that you want to look up. Yeah, so wrapping up, what did we do? Let me go back to what were the contributions. So the idea like, again, that sort of motivated this work was that we saw a lot of places where you had different fields, where you had foreign arithmetic that had to be put in zero knowledge proofs. And we showed a bunch of different techniques in which these zero knowledge proofs can be made more efficient by just removing this foreign arithmetic from the field and using other tricks for playing with it. The first one was using rejection sampling. And I think this technique is used a lot in lattices because there you need to prove that a vector S is small. And I think it can also be used to make really efficient arguments in the discrete log setting. And maybe we sort of forgot about it in the community, but one example where I think was really useful and allowed us to save a lot of computation over, I don't know, generic proof systems like Fry, etc., is to use it for proving that two commitments are to the same value. The second techniques that I thought was that we think is sort of nice and can be used also elsewhere is that it is possible to trade off one scalar multiplication with a new hash evaluation. And the way to do it is to put a Schnorr proof for X, and then you have one additional commitment to prove the hash pre-image of. So again, also in here, you remove proving the elliptic curve formulae from the circuit, and instead you just prove hash pre-images. And the third way in which all these foreign arithmetic can be removed, and this was sort of widely known already in the community, I think, is by using lookup protocols. And with lookup protocols, again, you can check a correct function evaluations, and especially if these functions are Boolean, it is really easy to play with them and even to split the complexity of the table into smaller tables that then of which then later you can prove membership of. So yeah, this was roughly it. I am happy to take any question and also to go more into the detail of nitty-gritty tricks that were used internally to make things even more efficient.
Thanks for that. Yeah, just opening the floor to anyone else who might have some questions. Oh, I think Victor. I think feel free to just jump up. Yeah.
Yeah, this is really helpful. I'm looking forward to like diving into these in great detail and like there's a lot to learn here. Just like cool great tricks. But one thing I was wondering about with the linear time verifier, it's like basically offloading operations to the verifier is a really useful trick. I guess one of the context I'm thinking about though is like when you want to integrate this proof into larger proofs, especially when you want to start doing recursive compression of proofs. I guess basically then the verifier becomes another circuit. And so basically I'm curious about how to manage that. Basically, if you're throwing your finite field over operations out to the verifier, but the verifier is also a circuit, then it's like you might end up back in the same situation again. Does that make sense?
Yeah, it makes sense, and it's a really nice question. Thank you. I think in here the idea would be that I haven't really thought about the recursive setting also because even if you read the paper, we're really using like a legacy technology, and I think part of the reason was that when I was initially thinking about it was with Trevor, and Trevor sort of was very familiar with Schnorr proofs, and I was trying to keep everything to that level of simplicity, so without throwing in any sort of recursive snark or any fancy construction. But I think also the idea here is that we try to bring to have a little gadget that sort of maps AES to a Pedersen commitment. And so I think the idea here is that then you can prove separately whatever you want about the AES proof, about whatever it's about the AES encryption, by just proving things over the Pedersen commitment. And it's really easy to re-randomize Pedersen commitment. You just add a new blinding factor to it. And so I think the idea is that maybe whenever you prove many things about them, you end up only having to prove things about M and K as Pedersen commitment, and you sort of keep the same sort of a proof separate, the same proof gadget for the ciphertext outside. I don't know if that is satisfying, or if you think like it would really be needed also to reprove everything because you want to make it unlinkable, or if having a separate proof, you know, for proving properties about M and properties of the ciphertext would be sufficient.
Yeah, no, I think there's a lot to think about here. And I think that the focus on using like much simpler primitives is really valuable. yeah, I'll be thinking about this some more.
And I think like that what was sort of seen with the Uvetana folks is that, again, like trying to also bridge with the rest of the research, is that the XOR operation, you don't, and all the linear operations, you don't really need to do them if you're working over a binary field, which is a really nice result, because then you can just remove all of these tables and you're just left with the S-box operation, which, by the way, I think sort of, sorry, like trying to bridge also with the other research fields. In the MPs in the head community, the S-box operation can also be done with a polynomial of degree 7. So I wonder also, more in general, if there are tricks from the MPs in the head community, which has really been optimizing AES for their purposes, if there are tricks that we can also inherit in our community. But this is more of an open question and a long-term thing.
Great. Anyone else have something to share? Seems like people got what they came for. Very cool. All right. Thanks so much for this presentation. Yeah, and thanks to everyone who came through. Cheers.
Thank you. Bye-bye.